Today we're going to look at section 10.2, which is all about the hyperbola. So we're going to be graphing hyperbolas today, specifically when we are centered at the origin, and then we're going to be writing equations of hyperbolas in standard form. So the definition of a hyperbola is hyperbola is the set of points in a plane, the difference of whose distances from two fixed points called foci is constant. So as you can see from this picture here, notice that essentially a hyperbola is kind of like a parabola looking shape, but there are two of them going in opposite directions. Notice this time the foci are going to be inside of the parabola looking shapes. It says the line through the foci intersects the hyperbola at 2 points. We call these vertices. The line segment that joins the vertices is the transverse axis. So while we were talking about the ellipses, we would say like major or minor axis. Well, here we have the transverse axis is going to indicate that we have the vertices. The midpoint of the transverse axis is the center of the hyperbola. So here's a quick sketch of the two different drawings that we will make. So notice that we've got our hyperbola on the left where they're opening left and right. So on the x-axis, notice that that bolded red line is the transverse. And notice that what I have highlighted in yellow, we call the conjugate axis. So like I said, it's a little bit different from like the major and the minor axis. Now we've got the transverse and the conjugate axes. Notice that on the right, we have the hyperbola opening up and down. So the red bolded line there, once again, is the transverse axis, while what I have highlighted in yellow would be the conjugate axis. So here is our two different equations for standard form. Notice that we are dealing with two fractions. This time they're being subtracted and they equal 1. So there are some similarities to the ellipses that we've talked about, but this time to be a hyperbola, we have to be subtracting the fractions. Also notice that these two are similar with the fact that a squared and b squared are in the same spot. A squared is always first, b squared is second. It is the x and the y values in the numerator that are flipped around. So when the a squared term is under the x, that tells us that the hyperbola opens horizontally, or basically, left and right. When we have our a squared term under the y value, that's when our hyperbola is going to be opening vertically, so up and down. And hopefully that makes sense. X-axis moves left and right, so that's why we'd have our hyperbola opening horizontally. The y-axis moves up and down, and so that's why our hyperbola opens vertically. Similar to the ellipse, our center would be at the ordered pair HK, and we take opposite signs for both. To find the foci, we're going to use the equation of c squared equals a squared plus b squared. So this time it is the Pythagorean identity, or Pythagorean theorem. So let's look at a couple of examples where it's asking for us to find the vertices and locate the foci for each of the following hyperbolas. So once again, we know it's a hyperbola because we have two fractions being subtracted and it equals 1. Remember, whatever number is first in our denominator will always be our a squared term, and then b squared will always be second. So it is going to be important to identify a, b, and c. So take the square root of both those numbers. A is 5 and b is 4. To find our c, we once again are thinking that c squared equals a squared plus b squared. So that means that I want to add 25 and 16. So c squared equals 40. When you take the square root, I can't simplify that any further. So the square root of 41 would be that value for c. Notice that the value or the letter that I have above the a squared term in this first problem is x. So that tells us that our transverse axis is dealing with the x-axis. And so that tells us that we'd be opening horizontally, which means that to identify the vertices, because there is no number with the x and the y, our center is just 0, 0. To find the vertices means that I'm going to have to be moving left and right to fall on the x-axis. So that means that from 0, 0, I'm going to add that a value of 5 onto the first number in my center. So that would be 5, 0. And then I'm also going to take the A value and subtract it from the center. And so that would be -5, 0. To find the foci, well, the foci are going to be lined up on the same transverse axis as the vertices. So once again, because our x-axis, our hyperbola is opening horizontally, that means the foci are also going to be moving horizontally from the center. And so because our center is dealing with 0, 0, and our C value helps us get our foci, I'm going to be adding and subtracting that square root of 41 onto the first number in my center. And so because I'm adding and subtracting it from 0, we have our two ordered pairs, both positive and negative, square root of 41, 0. And those would be our answers. So then if I'm looking at part B, once again, our A squared term will always be first in a hyperbola. B squared is always second. So identifying A, B, and C. Hopefully we notice that it's going to be the exact same values. Take the square root of 25, you get 5 for A. 4 would be for C. And so then that's still going to give us the square root of 41 for C when we are doing our C squared equals A squared plus B squared. But notice that the term that is above our A squared term this time is Y. So that means that our transverse axis here is going to have to be on the y-axis. We're moving up and down. So that tells us that when I want to identify my vertices, I'm looking at changing the second number in my center, or the y value in my center. And just like the first example, there are no numbers with the x and the y in the numerator, so our center is technically 0, 0. So that tells me that for my a value, I'm going to be adding it onto the second number in my ordered pair, as well as subtracting it from the second number in our ordered pair. And same idea with the foci. From the center, I'm going to be adding and subtracting the square root of 41 to the second number in my center. And those would be my answer. We have asymptotes when we're talking about hyperbolas. I threw in those pictures up at the top right again because notice that how those parabola-looking shapes are being formed. Notice that they're getting closer and closer and closer to those dotted lines, and those dotted lines are asymptotes. When you have an asymptote, it is getting closer and closer to it, but it's not going to touch or cross it. So when we're talking about our x term being above the a squared, which tells us that we would be having a horizontal transverse. Notice that my formula, really what I have to look at is the second part of the ordered pair, where notice that my slope says positive and negative b over a. And hopefully that makes sense, because think about slope. Slope is rise over run. If I was to look at, well, what value is moving up and down in this picture on the left, notice that this value right here, moving up and down from the center, that's my value for B. My transverse, remember, is always dealing with my A value. So A is moving left and right, so that's the run part of my slope. So that's why it would have to be B over A. If I'm looking at the fact that in the second hyperbola, if the y term is above the a squared, well, that tells us that we are opening up vertically. And so if you're looking at your slope, well, notice slope once again is rise over run. And so to move up and down this time, that is dealing with the a value because our transverse is vertical. And so that's why then the run value horizontally would be b. So that's why it's a over b. Let's look at a couple of examples on how we actually graph. So here I already have my equation, x squared over 36 minus y squared over 9 equals 1. That's already in our standard form. Let's identify a, b, and c first. So the first number is always our a squared term in the denominator. So when I take the square root, I get 6. 9 represents the b squared term. So take the square root and I get 3. When I then want to identify C, I'm thinking C squared equals A squared plus B squared. So that means I'm adding 36 and 9 together. And so when I do that, I'm going to get, 45, but that represents C squared. So I have to take the square root, and this simplifies. Notice that that's 9 times 5. 9's a perfect square. So my C value is 3 root 5. To identify the transverse axis, we look at the term that's above the a squared and notice that it's x. So it's going to be the x-axis, or you can just say x. In this case, that means I know that I'm going to be thinking about moving horizontally. My center, because there are no numbers in the numerator with the x and the y term, it's just going to be 0, 0. So just like we practiced, our vertices, because I know that I'm dealing with my transverse on the x-axis, means that we are going to take the first number in our center and add and subtract the a value from it. So that gives us 6, 0 and negative 6, 0. Okay, so then same idea with the foci. We're going to be adding and subtracting the c value onto the first number in our center. And so that gives us both a positive and negative 3 root 5, comma 0. All right, so before I list the asymptotes, I'm going to start kind of plotting some points here. So our center is at 0, 0. I know that at 6, 0 and negative 6, 0, that is going to be the vertices. So even though I didn't have us identify it, the b value then means I'm moving up and down from the center. So up and down means that would be at 0, 3 and 0, negative 3. And that's what helps create that conjugate axis. And so the vertices and the points on that help make the conjugate, that's where you're going to then use, and it's going to create this rectangle or this box that you can kind of sketch in really quick. Okay, so I've created this box here based off of the vertices and the points from the conjugate axis. So then once I have that, I can plot my foci. So if I kind of approximate, what is 3 root 5 approximately? So the positive value would be then 6.7. So then obviously negative 6.7 would be the other one. Your C value should be the biggest number. So it should be bigger than A. So that means that it's kind of squeezing kind of small here, but notice how it's past. It's getting closer and closer to 7. It's outside of the box. All right, so then now I can actually draw in my asymptotes. I can draw it in nicely based off of the picture of the box, because from the center, I want to go to the corner of the box. So notice how that takes me there. And then I can kind of, if I do it nicely, I can kind of extend it. But hopefully we notice that, hey, you had to move up 3 and then over 6. So technically 1, 2, 3, I had to move up 3 and then 1, 2, 3, 4, 5, 6. So if I extended that correctly like I should have, then it goes over here to 12, 6. And then same thing, if I go down 3 and over 6, that creates this portion of my asymptote. So if I go down 3 again and over 6, that would help me finish it out outside of the box. So hopefully then we're okay with the fact that because there is a center of 0, 0, then it's y minus 0. So that's why it's just y. And then we're going to have both positive and negative. So once again, in this case, to go up first, that was the b value. That's a distance of 3. And then the a value was 6. Well, 3 over 6, we can kind of simplify that down to a half. And then that's multiplied by then x minus whatever the first number for our center is. But since it's 0, then we would just say x. Okay, and so it's the same thing if I do it then the other way. If I go down 3 and then 6 to the right, notice how that fills in my asymptote there. And then if I go down 3 and over 6, it takes me here. So then I can continue extending that asymptote. And then it takes me then on the other side, if I go up 3, but then 6 to the left. And then if I go up 3 and 6 to the left, there's the rest. I need to have a good asymptote drawn because that's going to help me create the shape of my hyperbola. So then our final step is, because I know we're dealing with the transverse on the x, wherever my foci is, remember my parabola looking shape, the foci should be inside of it. So from those vertices of 6, 0 and negative 6, 0, I'm going to be creating now, in this case, a parabola looking shape going to the right where it touches the vertice at 6, 0, and then it's getting closer and closer to those asymptotes that I drew. And then same thing on the other side. Notice that my once again, my foci is inside of that parabola looking shape, but then it's the same thing on the left. I'm going to be getting closer and closer and closer to the asymptotes that I drew, but I have to have it going through that vertice at -6, 0. And there is my graph. So if we look at one more, notice that my equation does not have it in standard form, because to be in standard form, it has to equal 1. And right now, my graph, it says y squared minus 4x squared equals 4. So to make it not equal 4, I'm going to divide every single term by 4. So then that gives us the equation of y squared over 4 minus, well, if it's 4 divided by 4, then it's really just x squared over 1. And now that equals 1. And so if I want to identify a, b, and c, once again, the a squared term will always go first. So the square root of 4 is 2. B squared is always going to be second. Square root of 1 is 1. C squared, remember, is a squared plus b squared. So if I add 4 and 1, I'm going to get 5. So that means c is the square root of 5. Because our y value is above the a squared term, that means that it's going to be the y-axis that represents that transverse axis. So that means that our hyperbola should be opening up and down. Because we don't have any numbers in the numerator with the x and the y's, our center is just 0, 0. But then to find our vertices, we're taking the a value and we're adding and subtracting it onto the second number in our center. So that means it would be 0, 2 and 0, -2. And then same idea with the foci. We keep the first number the same. I'm moving up and down, so it would be both a positive and negative square root of 5. So then if I start plotting my points, center 0, 0, I know I have to go up to 0, 2 and down to 0, -2. Remember, I want to finish creating that box, and so that means I have to use the b value to move left and right to help form that conjugate axis. So 1 to the left and 1 to the right. I've got a pretty small box here. So this box right here is going to help me create my hyperbola. Okay, so then notice that my foci, if I was to approximate what's the square root of 5, well, that's approximately 2.2 and -2.2. So I know that it's a little bit outside of the box going up and down. Okay, to find my asymptotes, remember we are connecting from the center to the endpoints of the box. So notice how I'd have to go up 2 and then over 1. And so that's why in this case, y minus 0 as part of my center would just be y. Then that equals both positive and negative. Going up 2 and over 1 means that 2 over 1 is just 2, so a over b. And then it would be times the quantity of x minus our h, but since 0 is the first number for our center, I'm just going to have x there. All right, so that means that my slope is 2. So if I just have a couple of points here, if I start connecting, notice how it goes from the center to that corner of my box. And then if I keep extending past, because I know I'm going to need to know the shape of my hyperbola. So there is one of my asymptotes. And now I'm going to do the same thing going on the other side, up 2 and 1 to the left. Tells us that we're going to have an asymptote starting like this, going through the center, and now to the other corner to have something that looks like this. And so then from the vertices at 0, 2 and 0, -2, notice how I'm going to create my shape where it is, needs to go through the verticing, not the foci. It's getting closer and closer and closer to our asymptotes without it actually touching or crossing. And there is my graph. All right, so today we're focusing specifically at the center of the origin. So your center should always be 0, 0 today.